Thank you, Noreen, and welcome everybody to Grand Rounds. And I want to start by thanking Dr. Abramowitz for presenting the last Grand Rounds for the biomarkers. Thank you so much. And um,
Hello.
Join the meeting.
let's go to the next slide. Hopefully, okay, well, it's not progressing. So let me just do this. Here we are. This is my disclosure. And if anybody else wants to fund me, tell them to come and talk to me. And so today we have a few things to cover. Really excited to cover this with you. First, we're going to talk about the different Alzheimer's biomarkers. We're not going to do a lot of details because Dr. Abramowitz has covered that quite well the last time. And then my main role today is to introduce to you different biosignals, EEG in patients with cognitive decline, discuss the role of EEG and how abnormal EEG findings correlate with cognitive decline. I'm really excited also to bring in our medical students who've been working with us, some of them for as long as 6 or 7 years on a project that we looked at, looking at EEG, how it correlates with cognitive decline. Next, we're going to talk about the role and challenges of EEG as a biomarker and also ERP is evoked related potential. Last, we're going to discuss how AI, machine learning, is changing data processing in functional biomarker like EEG and ERP. And we're going to wrap this up with talking about real life clinical cases. Uh, really excited to do that with you today. So so how big of a problem is Alzheimer's? Alzheimer's is really big. As everyone knows that 1 in 3 seniors do die of Alzheimer's. Uh, and it affects almost 7 million Americans. It's very costly as well. In 2024, it's estimated that it's going to cost the US $360 billion. If you think about it, that's more than the GDP of a country like Philippines. So if we really want to make a mark on our nation, we really have to. This is one of the things that we can really do to get the greatest return on investment. Of all the top 10 things that happen in top 10 diseases, this is the only top 10 that we haven't really made great progress. So I'm really excited to talk about some of the exciting things that are going on. So Dr. Abramowitz last time talked to you already about the fact that by the time that our patients have memory loss, by the time that they have mild cognitive impairment, for example, MCI, uh, what really happened, the accumulation of proteins, the amyloid and the tau, has really happened years before, as long as 20 to 25 years before they actually have memory loss. So when the neuropsych test or the MRI shows abnormalities, there's a good chance that they have been undergoing the pathologic change for years, starting with the amyloid, the purple, and then the tau, the orange colored. So what, so all we're doing right now is just trying to play catch up. What do we really need to do as a scientific and medical community to really make a difference? So one of the things that we're really excited to discuss with you is looking at instead of playing catch up. So all of the symptomatic trial, if you look on the right side of the screen, the symptomatic trials that we've been doing is trying to remove the amyloid plaque, whether it's Leqembi, aducanumab, what we have, or prevent tau formation. Those are secondary prevention. So remember that the pathology really happens years before, as long as 25 years. How do we really get to the stage where we could actually stop the plague from initiated in the first place and stop the tau, the tau process early in the process to the hyperphosphorylation before they get to tau aggregation? What do we need to really do? How do we make a difference? Is there a way, or so so the neurology committee has been working on this for years. I just remember as a resident, we were taught that it's too late by the time that you get to this. But the answer is, how do we get there early? So the next question we really need to address is why? Why do we want to detect them early? What is really the benefit? Is there anything that we can really do about it? So yes, of course there is. Early allows for early care planning and coordination, and diagnosing them early also allows for clinical trials because that's really how we can really develop better treatments through developing better therapies, and it also allows opportunities for lifestyle intervention, that has been demonstrated to reduce incidence and rate of cognitive decline in this patient population. So if it's beneficial, so so let's talk for a minute about challenges of how do we detect them early. So let's talk first about cognitive diagnostic tool. So we have an array of them, the neuropsych test, MMSE, MoCA, what have you. I have a patient that, so we have a number of clinical trials that are going on here. A patient that came in and just 2 weeks ago, and his MMSE is declining rapidly. I was wondering what happened. I asked him, "What's wrong? Why is your MMSE declining so rapidly? We're trying to. You're on a clinical trial. We're trying to get some accuracy." And he said, "You know what? The room is too hot, or I didn't have breakfast." So cognitive testing, diagnostic to MMSE, MoCA, what have we, are really very subjective. They're really prone to a lot of assessment anxiety, and they're really insensitive to early stages of disease process. And if they keep doing the MMSE, they're going to get practice, they're going to get better at it. There's also educational and cultural basis. I have a lot of Mandarin, Korean, and Japanese speaking patients. How do you make them do that? What is the cultural basis? And it really does need good verbal and written communication, for them. So as America is becoming more diverse, we really need to look at what other ways can we approach this? So NIH and NIA have been looking at these issues for a number of years. Prior to 2011, our main goal is to really diagnose this, really get a pathology. You will always look for that nice amyloid plaque in the brain, But the fact is that by the time you get to those plaque, it is really too late, to do anything. So by 2011, NIA realized that we need to do something else. We need to incorporate biomarkers, amyloid biomarkers into our diagnosis. So since 2011, there has been a big change, big a push for biomarkers. In 2018, NIA, Alzheimer's Association, they met again, and they had a framework at that time. They basically decided that biomarker is really the way to go, because by the time memory testing is so subjective, first of all, and also by the time that they get to memory loss, it's really too late. If we really want to make a difference, we need to focus on defining Alzheimer's disease as a biological entity defined by biomarker. We don't really care if you have memory loss. The biomarker is becoming more and more important. So the independent of the clinical spectrum. So just going back, just an overview, there are several different biomarkers. We have the amyloid. Just remember that Alzheimer's is not the only amyloidopathy. You have a dementia of Lewy body, cortical basal degeneration. Alzheimer's, you've got to have amyloid and tau. Remember tau, you also have PSP, progressive supranuclear palsy, cortical basal degeneration, FTD, frontotemporal dementia. That's another big one. So you got to keep in mind, biomarkers is not just for Alzheimer's, whether it's amyloid or tau, there's some overlapping. And then obviously the other big one is synuclein synucleinopathy with Parkinson's, dementia, Lewy body, MSA, multi-system atrophy. So keep that in mind. So let's just focus for a minute on biomarkers here. So in 2018, NIA basically came out with the ATN biomarker profiles and categories. Basically, A for amyloid, T for tau, and N for neurodegeneration. And C is clinical for dementia, And again, by the time we feel that it gets to dementia stage, we really want to get them early, want to diagnose them early. And so early on, you could just have changes to the amyloid A plus, T minus, N minus, and then as next tau becomes positive, and the neurodegeneration meaning the MRI is positive, and then NIA starts breaking them down into 3 biomarker categories or 8 different groups. So again, you're going to see that Alzheimer's disease is becoming a continuum, a spectrum. It's no longer just based on memory loss. It is really based on a biomarker. So the Alzheimer's biomarker really started as far back as 2007. I remember that when CSF and amyloid PET came out, there was a lot of excitement. So amyloid PET came out around 2006, 2007, CSF biomarkers, and then amyloid PET, tau PET came out in around 2016. So in CSF biomarkers, you look for decreased concentration of A beta 42, the ratio of Aβ42 and 40, you look for increased concentration of phosphorylated tau. And same thing with the blood biomarker, which we're going to talk in a minute on. And PET scan, obviously, you look for increased tracing binding of beta amyloid PET or increased binding to neurofibrillary tangles. So what can we say about Alzheimer's disease biomarkers so far? Well, we know that the presence of amyloid really increases the likelihood of developing Alzheimer's, but it is also noted that most individuals with brain amyloid will not develop Alzheimer's. And we have to really clarify that not everybody with amyloid has Alzheimer's. So let's take, for example, CSF, which is what we're doing for the last probably about 7 to 8 years. We've been sampling our patients, Alzheimer's patients, CSF biomarkers. So CSF biomarkers are what we call structural or diagnostic biomarkers. Same thing with PET biomarkers. They are looking at measuring amyloid and tau aggregation. And they're very increasingly used in research and studying more recently being used as a clinical diagnostic tool to decide whether a Leqembi is suitable or not suitable. So it is increasingly moving out of the research realm into the clinical utility realm. However, there are a few challenges. For example, I've been doing CSF for the last 7 to 8 years. The limitations are, keep in mind that if we take 100 elderly patients with no memory loss, about 20 to about 3 of them will have amyloid positive PET scan, and they don't have memory loss. How do you explain that? So that's number one. Number two is that if you remove all the amyloid, just like the Leqembi trial, you remove 97% of the amyloid. But the memory only improved by 27%. So how do you explain that? So there is not a good correlate. So amyloid depositions, tau aggregates deposition are biomarkers, but are they real biomarkers, or are they surrogate biomarkers? The relationship with cognition is still unclear. What we can really conclude is that although necessary, amyloid isn't sufficient for Alzheimer's diagnosis. The other biomarker that's really popular that's coming out is what we call fluid biomarkers. Fluid biomarkers consist of 3 kinds, at least 3 different kinds. So we're talking about blood biomarkers, which are really, really gaining a lot of traction, and just because it's scalable, it's easy to get. Why do you want to do a spinal tap? Why do you want to put somebody in a PET scan when potentially you could get blood biomarker? But so blood biomarkers are different kind. You can go after the neurodegeneration with the neurogranin, or NFL is neurofilament. And then for inflammatory markers, the popular one are YKL40, And then progranulin is another popular one, looking for inflammation biomarkers. And those are rather popular, and gaining a lot of traction. There are challenges with fluid biomarkers. There are three challenges. Mainly is the blood-brain barrier is the challenges to fluid biomarkers. Why is it so difficult to develop blood biomarkers while we have good biomarkers for PSA, for colon cancer, for ovarian cancer? Why is it so difficult? Because of blood-brain barrier. Number one is whatever is happening in the brain, there's a huge barrier and very little of it seeps out to the outside into the systemic. Number two is whatever the degradation in the systemics, whatever seeps out, it gets degraded in the plasma very quickly. And then the third issue is whatever that you see in the plasma, it could be a sign of systemic damage rather than a CSF damage. So these are the challenges that the people who are working on the blood biomarkers, they really have to overcome. But it's very exciting. I am really excited about what they're doing, and it's really getting traction. My hope is that within the next, who knows, maybe 5 to 10 years, we will have a blood biomarkers for Alzheimer's. I hope so, anyway. And then obviously we have the CSF biomarkers, and also increasingly there's biomarkers that we can get from the retinal neurofilaments, and optical biomarkers from the eyes and things like that. So those are other exciting fields that what we call fluid biomarkers that is being developed, and I'm really excited about it. So what is the FDA's perspective on surrogate biomarker? Surrogate biomarker is defined as a measurement of physical sign that is used in therapeutic trial as a substitute for clinically meaningful endpoint. So it can be proposed as potential candidate to define the effectiveness, but as of this date, no such biomarkers have been adequately validated as shown to predict the effect on the treatment and clinical outcome of interest. So we still have some work to do in terms of biomarker. We got a lot of work to do. So why is surrogate diagnostic biomarker not the same as a cognitive loss? So if you look at surrogate biomarkers like amyloid or tau, these are tissue changes. This is cell and tissue changes measured by amyloid PET or the CSF. But cognitive loss is really a clinical function. It's a synaptic function. How do we, so on the article by Jeff Cummings in 2019 that I thought was interesting, he also realized that cognitive loss is not the same as a diagnostic marker, surrogate diagnostic marker. Because cognitive loss is a circuit problem, it's a functional synaptic problem. So why the disconnect? Disconnect is that there's a good chance that synaptic functional loss in the neuron, in the neuronal level, actually happens way before the protein actually gets, you get the protein's deposition. So I really like this article that noted that although the neuropathologic hallmarks of Alzheimer's are extracellular amyloid is extracellular and tau is intracellular, the best correlate for disease progression is actually synaptic loss. So synaptic dysfunction can actually occur years before the protein deposits. And cognitive impairment only manifests when the pathology spreads throughout the brain. So synaptic function loss occurs years, at the presynaptic as well as the postsynaptic level, whether that's synaptic vesicle release inhibition, endocytosis inhibition, recycling inhibition, or endocytosis, impaired endosomal sorting, those occurred years before the protein deposits. So where is our missing link? How do we approach this if surrogate biomarkers is not directly always the same thing as a cognitive loss? Where do we go from here? There's another group that's also looking at, and in California, the advanced brain monitoring folks looking at So again, the clinical symptoms, cognitive loss, and you have the pathology here. So what could be the missing link here? So could EEG biomarkers, which is a measure of synaptic functional, be the missing link? So let's talk for a minute about EEG findings in dementia. So EEG findings in dementia, for the most part, are very non-specific. And we realized that for years. And I put the pre-AI era because I think AI is about to change things. So we already know that in Alzheimer's patients, that progressive slowing, and in Lewy body dementia, that's mixed theta, alpha, and periodic wave, and in Parkinson's, there's mixed alpha slowing. Huntington's, there's low voltage. PSP, that's low voltage. So they're very rather non-specific, and for the most part, not that helpful. you know. Um, so what is about to change? So we have looked at this for the last 7 years, and I was curious because of my background in EEG and cortical neurophysiology. I was curious, and I had a group of students who looked at it for the last 7 years, and I'm going to have one of the students to present the findings that we looked at in the last 7 years. So I'm going to invite Nathan Kim, one of our students, who worked on this project since his undergrad years, and he is right now a third-year medical student at Jefferson. Nathan?
Okay, thank you, Dr. Liao. So yeah, I'm just going to talk a little bit about what EEG is and then a little bit about some of the research we're involved in. And we're also going to be having some of the other medical students who are also been involved in the research talk a little bit too. So what is EEG? So EEG, or electroencephalogram, is basically a test that we can use to measure the electrical activity of the brain. It allows us to look at the voltages generated by the neurons over pretty much a large area of the cortex. And we're able to look at things such as the frequency and amplitude of the waves, as well as looking at the specific location. And some of the main advantages of EEG is number one, that it's inexpensive, and number two, that it's non-invasive. And so this can play a good role in possibly the preclinical stage of Alzheimer's. Because we know, as Dr. Liao mentioned, we are still looking for a good biomarker to help detect it. Next slide. So this was the research study that we started, as Dr. Liao mentioned, like 6 or 7 years ago. This was one of the first posters we presented. And basically, we were looking at if EEG could be used to help predict the onset of Alzheimer's disease in patients at the preclinical stage. So that was defined as basically these patients are healthy individuals with no evidence of Alzheimer's disease. And so we had all these patients who had a MMSE score greater than 28. And this was a small cohort of only about 18 patients. But what we did find, so what we looked at was patients who had data regarding their ApoE genotype. And so ApoE is basically a special gene that's been shown to play a role in a person's risk of Alzheimer's. So there's three different alleles that you can have. The E2, which is associated with a lower risk of Alzheimer's disease. The E3, which is just no change. And then E4, which is associated with the increased risk. And so what we found was that it did seem to patients who did have an ApoE4 allele present did seem to have a higher likelihood of displaying abnormal slowing on their EEG compared to those without. Next slide. So we recently published the full-length manuscript of this study, and we were able to collect data on more patients. So this one involved 43 total participants. You can go to the next slide. And basically what we found was that temporal slowing, like I said, same thing. It was associated with more likely to be seen in patients with an ApoE4 allele present versus not. However, these results were not statistically significant, but given the advantages of EEG being non-invasive and cost-effective, that we strongly believe that we should still be pursuing research in this area. Okay, next slide.
Thank you, Nathan.
Yeah.
As mentioned, great job. And Nathan's group worked on this for the last 7 years. Nathan started this project as his first year undergrad, and there was a first year med student that started this project with me. I think she's a third year resident right now. So it took us a total of 7 years to get this project done. Can you imagine that? So what? Thank you, Dr. Abelwoods. What is the challenge? EEG has significant challenge and limitations with EEG signals. For example, EEG signals are small, and it varies between individuals. Even for the same person, it changes over time. Lots of noise and artifacts. And visual interpretation is difficult, tedious, long, costly, and not easily accessible. And visual is not, EEG signals are not the typical data that people like to look at. People like to look at images, charts. So a typical electrophysiologist, like myself, we have to do at least 4 years of neurology residency and then 2 years of EEG fellowship to read EEG sufficient to do that. So it's difficult to find people to do this. I was very fortunate to find Dr. Bimla to help me. So just to give you a perspective of how challenging this is, if you listen to a neuron's action potential, it's just like listening to a one-person interview. If you're listening to a group of neurons functioning in a local field potential, it's like trying to listen to someone from a busy press box. If you're trying to analyze an EEG signal in the brain with all the neurons all firing together, it's kind of like trying to listen to a person in a crowded football field. That's probably why it took us 7 years to do this. So it wasn't easy, but thank goodness for this wonderful medical student. They persisted. And I was so afraid that Nathan is not going to even get a publication before he graduated. So thank goodness Nathan got a publication out. So it wasn't until about 3 years ago, I was doing a study, an NIH-funded study on phosphonematoin, which is a study to look at repairing synaptic function in neurons in patients with moderate Alzheimer's. So you can see that they were measuring cognitive function, ADAS-Cog11. So patients on purple is the on drug, and patients declining on the placebo. But I was curious. They were actually also measuring an EEG signal, ERP 300 evoked related potential, and it shows that patients on the drug, their evoked related potentials are improving. I was shocked. I said, "Oh my gosh, they are doing this, and how are they doing this?" You know, and so I went back and did some research, and I found this wonderful people, and in California, that is harnessing the power of AI to look at EEG signals in this group of patients. They are working on a project called Beam, and which I'm going to let our students explain that to you as well. So Beam emerged from a research support by NIH since 2016. There's different groups. The project has been ongoing at Mayo, Harvard, Scripps, University of Toronto, and and then I contacted them, and the rest is history. Here we are. I'm going to let our group of students who are working on our BEAM projects, collaboration with advanced brain monitoring folks in California, uh, explain.
Thank you, Dr. Liao and Nathan, for that beginning to this presentation. I'm going to start with what is BEAM? Well, what does BEAM stand for? It stands for Biomarker Electrophysiology for Advanced Brain Monitoring. It is a biomarker-based EEG platform utilizing AI algorithms trained on a database of 10,000 EEG recordings and a library of biomarkers to map progression of cognitive decline. BEAM combines EEG and neurocognitive testing, both active and passive, visual and auditory, to assess attention, memory, and emotion. BEAM's algorithms address some of the challenges with this data, such as with EEG data, such as laborious data interpretation, among many other challenges. But BEAM aims to address those. So for example, next slide. BEAM takes EEG to quantitative EEG. BEAM takes the classic squiggly line patient EEG data and analyzes it using standard resting state techniques and transforms the results into easy to read graphs and tables with value comparisons to healthy and cognitively impaired groups, thus giving clinicians and researchers quantitative data to map cognitive decline across a variety of dementias. So BEAM has some extensive resting state capabilities. So I'm gonna, if you could do next slide real quick. Thanks. Analysis, so there's extensive capabilities that BEAM is able to do, and one is power spectral density estimation, which is basically analysis that demonstrates the power distribution and frequency domain for each individual electrode. And it also, BEAM also gives some time and has capability for topographical mapping. And basically topographical mapping is a graphical representation of cortex activity created by a software that codes wave frequencies in several tones of color and uses mathematical interpolation to calculate the wave activity in spatial points not directly under the electrodes, so in between. And thus creates a color gradation for such areas. So we can see the activity on a larger scale, looking at the, it basically shows on top of the head, as you can see, there's the little nose and ears. And BEAM also has capability to do connectivity measures. So connectivity analysis assess some similarities and differences in spectral power between electrodes over time. So if similarity is observed between two or more electrodes at a certain point in time, inferences of brain region connectivity can be made and vice versa for disconnectivity, which is especially important when it comes to, a variety of dementias where there may be some disconnect. And lastly, BEAM is capable of source localization, which source localization analyses assist in locating deeper brain structures responsible for surface EEG signals with utilizing predictive modeling constrained by understandings of neuroanatomy and neurophysiology. And to do that, BEAM uses a special software called Loretta, and it stands for Low Resolution Electromagnetic Tomography. And it provides a solution and ability to localize activity boundary and deep sources, which is especially important when we're needing to look at, cognitive impairment in diseases such as Alzheimer's disease and Lewy body. And
Okay, hi everyone. My name's Kira Varello. I'm a second-year medical student, and I'll just be talking about some findings from an important paper that utilized some of the techniques that Sarah was just talking about, specifically the power spectral density as well as the topographical mapping. So this paper compared these EEG markers to cognitive decline in Alzheimer's disease, which is similar to what our end goal will be when we're using the BEAM data. So the study found that MCI and AD groups both showed increased power in low frequencies. So you can see on the left side of this graph, and that's compared to age-matched controls, which is the blue line. At higher frequencies, the Alzheimer's disease participants showed increased absolute power in the same direction as normal aging, but with a larger effect size. So we can see that on the right side of the graph. Then to better understand these changes, they did the topographical maps, which just popped up. Thank you, Dr. Liao. So we're looking at the theta to alpha ratio. So we can see that the theta to alpha ratio is clearly increased in Alzheimer's disease. So the one on the far right with a lot of red and warm colors, it's clearly increased in comparison to the MCI as well as the healthy aging on the left side. The theta alpha ratio, it's one of the variables we'll also be looking at using BEAM. And I think Shay will talk about this a little more in the next slide. And then the last important finding of this paper is this bottom small graph with the orange. It just shows that the theta to alpha ratio was negatively correlated with MMSE. And this is consistent with previous studies. Although there was no similar trend in MCI, this is something that we're also going to be looking at with the EEG measures and MMSE. Thank you.
Hi, I'm Shay. So essentially, these EEG measures can really help to quantify the severity of memory loss from normal aging to MCI to Alzheimer's disease. So looking here at the alpha peak frequency, which is your fast frequency, lower values indicate like a slowing of the alpha, which is often associated with cognitive decline. So here in normal aging, you see this decreasing with age, as you go to the right here, but it's usually only significant in limited areas, so the occipital and temporal regions. And then when you progress to mild cognitive impairment, it's not too much significantly different. But then when you go to Alzheimer's, you see this really widespread and significant decrease all around here. And then your theta to alpha ratio, theta is your slower frequencies, and this is often increased in areas of cognitive decline. Therefore, your theta to alpha ratio will often increase. So here with normal aging, you see this decrease with age, usually widespread after about 60 years. And then in mild cognitive impairment, you see this begin to increase, usually only in the temporal areas. And then with Alzheimer's, you see this really widespread and robust, significant increase here. With mild cognitive impairment, usually you only see the theta affected first, so those slow frequencies before the alpha, which comes later. And then usually with MCI, it's often more localized before it progresses to that widespread increase in Alzheimer's. Next slide, please. And this is a really good table from the paper listing the different descriptive effects of AD and MCI compared to normal aging when looking at all of these various EEG measures, which has been really helpful when trying to think about what EEG variables we want to extract for our study moving forward. With resting state from the beam reports. So looking here again, it's pretty similar to what I just talked about, but you see the alpha peak frequencies here, which in normal aging, it decreases, but in localized areas. And then in AD, you see this significant widespread decrease again. And then with the theta powers, your slower frequencies in AD, you see this increased power versus normal aging. And then that results in an increased theta to alpha ratio that's really significant and widespread in Alzheimer's, as opposed to normal aging, where you see this decrease with age. So overall in AD, you see measures that are generally more robust and widespread with significant changes that usually oppose normal aging trends, except for that alpha frequency. And it'll be way more widespread in AD versus normal aging. And then in MCI, it might be more localized to the temporal regions before it progresses. Thank you.
Hi, I'm Michael, first year medical student, and I'm just going to take a look at this study here. So as we know, EEG has been used for investigating Alzheimer's, as we talked about, but it also looks at a wide range of conditions. So a few years ago, a group of researchers at Mayo and Advanced Brain Monitoring, which Dr. Liao was talking about earlier, looked at a group of about over 40 probands and over 50 controls, and they separated that proband group into Alzheimer's, Lewy body dementia, and Parkinson's. And then they took a look at various EEG signatures between those three groups with specific attention paid to Alzheimer's and Lewy body dementia. So if you look over at that left graph, which we've been looking at throughout this presentation, you can see that we looked at kind of degrees of slowing, and we see that in Lewy body dementia, as well as our Alzheimer's patients, we see increased rates of slowing. That's actually very increased in Lewy body dementia, as shown by that kind of more filled in box there on the lower left on that graph. And then what we did, which is where, again, kind of the true power of beam comes in, they looked at the three groups, the healthy controls, the Lewy body dementia, and the Alzheimer's. And if you look at that top row there, you can see spatially kind of where differences rise. So if you look at that top one, you see that there's reduced DR frequency across all three groups compared to the healthy controls, that being Alzheimer's, Lewy body dementia, which also included Parkinson's. And then you can also see on that third line how Alzheimer's has decreased DR prominence compared to both Lewy body dementia and healthy controls, as seen by that heat map with kind of more red, orange colors versus the blue in that bottom line. Next slide, please. So overall, this just is a comparison of different disorders, including Alzheimer's. And this is just another study that looked at something called IAF, which is individual alpha frequency. And this is associated with arousal, contrast, and attention in most EEG studies. And you can see that in healthy controls over time, in that right graph there, we'll see decrease. But in our Alzheimer's and our Lewy body dementia patients, we see that they're already decreased at baseline. So again, overall, this just shows that there's still more important work to be done, and BEAM can really help us in that regard. Next slide.
Hi, I'm Kylie. So I'm going to talk about ERPs and BCI. So we have been using brain-computer interface to evaluate ERPs in patients with mild cognitive impairment and Alzheimer's disease. Event-related potentials, or ERPs, represent the decrease or increase in the amplitude of ongoing EEG oscillations at a specific frequency in response to a certain mental command. Using BCI to measure ERPs, we hypothesized that the ERPs in patients with Alzheimer's will be different from ERPs in patients without Alzheimer's. Next slide, please. When testing ERPs, 4 different neurocognitive performances were evaluated: sustained attention, image recognition, emotional face recognition, and auditory oddball. These neurocognitive performances tested attention, executive function, memory, emotional biases, and cognitive processing to see if during these tasks there were distinct differences in ERPs between patients with MCI and Alzheimer's versus normal controls. Next slide, please.
Hello, everyone. My name is Jeanette, and I'm also a first-year medical student. So now this slide, I think, really exemplifies the power that BEAM has. It shows that with all of our raw EEG data, BEAM now has helped us to analyze this in a way that we can now look for specific ERPs, which would be indicative of MCI or Alzheimer's disease. In the first step, they'll help to average our EEG trials, as well as eliminating this artifact decontamination, which could potentially skew results and subsequently treatment options. And finally, producing a data readout sheet, which showed specific ERPs that could be of use, specifically the P300 wave in terms of latency and amplitude that we are then thinking could be more useful in future trials. Next slide. Now, with this target in mind, that P300 wave, advanced brain monitoring software has now helped us to identify a specific ERP signature associated with this wave that could be indicative of MCI, specifically an increased latency in that early component, which we refer to as the P200 wave, if you can see on the figure on the left, the increased latency, and also a subsequent reduced amplitude of that late component and this was reproducible between both normal patients as well as when we compared it to patients with mild cognitive impairment. Next slide. And finally, BEAM also provides our patient with what's known as a composite MCI score, which has a very highly predictive value of the severity of their individual MCI plans, as well as comparing to where they gauge in regards to normal patients as well as other MCI patients. And finally, BEAM was able to show that this results were validated both amongst patients as well as being reproducible throughout multiple studies and sites. Thank you.
Thank you. Thank you all the medical students who presented. I'm so proud of them. And I know that some of these topics are so new to them, but they really did a good job, didn't they? And I think our future in this area is in good hands. As older physicians like myself retire, so I'm really proud of them. I'm going to invite them to actually come into my room. The door is shut, so just come on in. So all this are great, all this data are great, but how does it really apply to real life clinical scenarios? So I just wanted to give you some example on just a patient that I saw this week alone. So I want to start, come on in, guys. I want to start by telling you about Mr. G that I saw this week. Actually, I saw him last week. Mr. G is actually a really, he's an executive. He runs a company by the shipyard here in Honolulu. High functioning executive, strong family history of Alzheimer's disease. His MMSE is 30/30, you know. But he is concerned, and more so his family is concerned that something is going on with Mr. G, you know. So what do you think? Is there a concern with somebody MMSE 30/30? Well, I got a feeling that if we put him through a neuropsych test, he's actually going to score really well as well. So I figured that something is going on because why do high functioning people tend to compensate? You know, even when the MMSE is 30/30, there could be something else going on. They have a high functioning. So even it takes a lot of depletion to even make a dent in the MMSE or even make a dent for them to be detected in the neuropsych test. So I decided to put him through a beam. And you can see that the green numbers are okay. The red numbers are not okay. So he does hit a few red numbers for eye open, especially in the EC-ITAR, which eye open individual theta alpha frequency ratio, which is very abnormal. It's 0.64, 0.61. And then the other is AO is for auditory eyeball stimulation, and one peak is 133/97. He's also abnormal. And the other abnormal findings is SIRP2 peak is sequence image recognition P2 peak is 203. So barely abnormal, but clearly we picked up something. So I did went ahead and scanned him. Let's see. So indeed, really, and what's more important is when we did his ITA, individual theta alpha ratio, this is his ITA, this is actual patient's ITA for Mr. G. And I compared him to the graph that was provided. What do you think he fits in? Clearly in the Alzheimer's group. You know, this is no longer a healthy control, not even an MCI. He's actually even way beyond the MCI group. And when I got his MRI, this is his actual MRI. I think you can appreciate his significant cortical atrophy. You know, also some white matter disease. His physical scores are up. His global cortical atrophy skills, Shenton's PAS-score scale on his MRI are all up. So as a result, I'm sending Mr. G for a biomarker sampling and also for potential treatment with potential disease-modifying treatment. So again, just to kind of go back, this is a normal high-functioning individual with normal MMSE, but functional, but probably was already synaptic dysfunction and picked up by being very clear on his ITA, individual theta alpha frequency ratio. You can see that this is in even beyond MCI in Alzheimer's disease stage. I wouldn't be surprised if his biomarker is positive. So I have another case last week of Mr. J. Mr. J is actually a friend of mine that I know really well at church. He's 73-year-old. Strong family history of Alzheimer's. He had an episode of transient global amnesia in 2023 last year. Was seen at Queens and sent home just very short period one day. His MMSE was 25, but I know that he's a very nervous guy and very anxious. So is this a normal aging or is this MCI? What do you think? So again, I'm not going to send him for a spinal tap. You know, I'm not going to send him for anything invasive or toxic. So I just did a beam, and all his scores are in the green. This is his actual score, and I think Mr. J is just a nervous guy who had an episode of transient global amnesia, and now a strong family history that is really concerned. And actually, I reassured him that all is well. Based on his synaptic measurement of his synaptic function, and send him home. I want to share a third case with you that I saw last week. YM is a patient referred from a geriatrician with a diagnosis of Alzheimer's, dementia. And when I saw YM, I had a few things, a few red flags went on. First, there was difficulty with speech. the language actually went out before the memory loss. There was clearly there was also a memory loss. YM is actually a anatomy professor, not here, retired, but just the initial presentation was difficulty with aphasia. So when I looked at his spectral analysis, also there was clear abnormalities in the focal, in the frontotemporal area, it really stands out. And when I looked at the MRI, there was clear atrophy in the frontal. This is the actual MRI in the frontal area more than the parietal area. So we were able to change the diagnosis from Alzheimer's to frontotemporal dementia. So this is just in the last 2 weeks, just the utility of Beam. So this is a real life case application. So for the sake of time, I'm going to go ahead and summarize. So in summary, we really do need better diagnostic tool. Our current cognitive test is subjective. Current surrogate structural biomarkers have limitations. In the past, EEG has significant limitations and non-specific, but I believe that AI, I'm so grateful for the collaboration with the AI company, Advanced Brain Monitoring company in California. I believe that functional biomarkers like EEG and ERP, which measures synaptic neuronal dysfunction, as the biological mechanism linking proteinopathies to clinical symptoms, has shown some promise. AI-powered application like Beam, a biomarker-based electrophysiology advanced monitoring, is really increasing its digital footprints and accelerating diagnostic accuracy for early detection, accurate diagnosis, quantifying severity, and also in the future, I hope to assess whether a treatment intervention is effective. So what's next? I'm really excited. This our wonderful team of medical students. They're actually standing right here too with me, and some of our EEG tech. We are continuing to collect data. Thanks to our collaborators, the Advanced Brain Monitoring company in California. We're working together to collect further data on genotype, CSF biomarkers, and clinical spectrum, sorting out FTD. I think that's a great potential using these AI applications for vascular dementia. There's quite a few applications already, good publications already in Lewy body dementia, and they have just shared another paper that they're presenting the next AIC on FTD, and we're really excited to work with them. And our project is on the website. Last but not least, I'd like to acknowledge our wonderful medical students and our neurologists who are working on this project, 5 of us, and including Dr. Abramowitz, Dr. Hagen, Dr. Corazana, Dr. Vijala, who has moved on. 4 of us are actually trained in EEG and cortical physiology, and we're very honored and privileged to be working on this project and to present these findings to you. And I'm going to introduce our medical students to you right now. So here they are, all sitting here. Let's see. Okay, there they are. Can you see them?
You guys did amazing. You did great. So did you, Dr. Liao. You did good too.
Thank you. Thank you. I think I really pushed the limit. Some of them, they really had to do a lot of studying. Was it stressful I'm sure it was very stressful to try to present on a topic that you're not familiar with, but I think they did a great job. I'm really proud of them, and thank you so much for the opportunity to share these findings with the audience here at the Psychiatry Grand Rounds. Thank you, Noreen. Thank you, Dr. Abramowitz, for being part of our team. We're really excited. Happy to take any questions.
I had a question. I don't know. I hope I can express it correctly. I'm surprised, like the executive, who did well on the MMSE, although I guess his family had noticed changes already, but the argument is that he has a lot of cognitive reserve, and so he's been able to function. and score well on the MMSE and whatnot. I'm surprised that the cognitive reserve didn't, like, I guess, protect him in terms of like the EEG findings. Like the EEG findings seem to be independent of any cognitive reserve, which I don't know if you have any explanation or thoughts on that.
Well, my experience has been that I see a lot of this high functioning people. I've seen physicians, I've seen dentists, lawyers who are high functioning people, and the MMSE are high, and yet we know that when we looked at the MRI, they have been undergoing degeneration for years. My guess is that they have a high reserve. You know, think of it as a water tank reserve. It needs a lot of depletion to even show something. You know, but at that point, you know, they may not even have a biomarker. You know, but I'm pretty sure that they do have synaptic dysfunction, you know, early on. Just keep in mind that synaptic dysfunction occurs years before the protein actually deposits. So I think there is a potential for, you know, biosignals that measure synaptic dysfunction like EEG and ERP for early detection, because this group are really tough because they really fool us. You know, I have quite a number of this high functioning doctors, lawyers. I mean, they really don't come in. They really don't seek any treatment until very late, unfortunately.
Do they usually think, are they usually brought in by their families, or I'm guessing, or versus the anxious one who is self-presented?
They're usually brought in by the families and children. Yes, that's correct. Yeah. But they have a good insight. They realize that something is going on. But yeah, I'm actually following several high functioning executives right now who are in similar, and obviously eventually we get to the biomarker stage and the spinal tap, and they're eventually positive. Now they're seeking some definitive treatment. Any other questions?
Really great presentation, beautiful slides. Great job, medical students, even MS1s. My goodness, very brave.
Let's show them. Let's give them a round of applause.
Brave.
The med students. Yeah.
Yeah.
Thank you. If there's no further questions, I'd like to thank Noreen and the Department of Psychiatry, Dr. Abramowitz, and the CME Committee Department for the privilege and honor of sharing these findings with you guys. We look forward to collaboration. Also, thank you to the advanced brain monitoring folks. I believe Amir is online, and thank you for the opportunity to collaborate and work with you guys on the data. Amir, do you want to say anything, Amir?
Sure. Hi. Our pleasure, Dr. Liu. Thank you very much for the excellent presentation. That was very nice. And we are also very excited to work with you. Now that I'm here, I do have a quick comment about the question that was asked about the cognitive reserve and why it would be different than EEG findings. And I just wanted to add to this point that it's not actually too surprising, because when you think about this, when you measure these EEG biosignatures, you are measuring millisecond level changes in brain activity, right? Whereas when you are looking at the performance, the cognitive performance of an individual, it would take them maybe seconds, or for something that's very fast, even a second, right? So it's not, it is conceivable to imagine that brain has time to use compensatory mechanism to perform the task. Whereas when you look at the EEG, you're precisely measuring at the millisecond, like some of these ERP measures, you're looking at 100, 200 milliseconds past the stimulus presentation, things like that. So I think it's a plausible explanation for why there's this disconnect between the EEG and the
yeah, because if you have cognitive reserve, you have to recruit other areas of the brain, and there's a time lapse in that.
Exactly.
I see. That makes sense. Thank you.
Yeah, of course.
Thank Thank you, Amir, for I totally agree. Yeah, it is amazing the work that you are doing, and thank you for the opportunity to collaborate and work with you guys.
Our pleasure. Thank you very much.
There are no further questions. Thank you, everyone. I'd like to dismiss, and thank you.
Thank you, Dr.
Thank
Liao.
Thank you, Dr.
Thank
Abrahams.
you.
Thank you, medical students.
Thank you.
Yes, thank you, medical
Thank you,
students.
medical students. Yes, very much.
Thank you.
Thank you.